Okay, so we were looking last time at the law for the magnetic field, and we had to stop because we ran out of time. We want to find the magnetic field of a circular loop. Now that doesn't look like a circle, but it's supposed to be. It's not one of my better circles. Matter of fact, it's pretty bad. Okay, so circle's going to have radius A, and we've got a segment delta L. There's a little yellow arrow here that you can probably see. It's just a short segment of this loop, right? So the delta B, according to this, is K prime I delta L cross a unit vector R divided by the square of that vector R, where R is what? R is a vector from the loop, from the segment to the point where you're measuring the current, or where you're calculating the magnetic field. Well, we're calculating the magnetic field at the center. If you want to calculate the magnetic field someplace else, have a good time. It's much more difficult. But because of the symmetry, it's very easy to get it at the center. Okay? Now we're going to do a straight line in a minute, and you'll see, and we'll have to use an integral to do that, and then you can think of what kind of integral you'd have to perform to do this at some point other than the center. Okay? Okay, well then the R vector is here. And I delta L cross R is clearly out of the board. Okay? And then it's perpendicular to the loop, okay, or the plane of the loop. And you got a right-hand rule, which says that if your fingers are in the direction of the loop, it gives us exactly what I just said it gives us, and we can see why. Okay, so what is delta B? I'm not going to put the arrow over because I'm just calculating the magnitude, right? Okay, well, delta L is perpendicular to R, right?
Yeah.
Okay. The magnitude of the vector R is A. That's how long it is that's how far it is from the circumference to the center, or from a point on the circle to the center. So we can make the note that magnitude of R equals A, and also magnitude of R over R is 1. I'm being a little inconsistent. I'm using double absolute value signs for magnitudes here, single for here, so I'll do the doubles here, right? So what is this reduced to? Well, what's this? This is 1. It goes away. So we just have magnitude of I delta L over A squared, right? And the magnitude of I delta L, I is constant. So it's just I times the magnitude of delta L, right? And the magnitude of delta L we just write as delta L with no arrow over it. So we get K prime I delta L over A squared. That's always in the same direction, always perpendicular to the plane of the loop. So to get the total magnetic field, it's this, right? You just sum up these things, and you're going to take a limit as delta L goes to 0, right? But first of all, before I do that, I'm just going to factor out the K prime I over A squared times the sum of your delta L's, right? Well, as the delta L's go to 0, the sum of your delta L's is going to be what? For the whole circle, the sum of all your delta L's is going to be
2 pi r.
the circumference,
2 pi
right? And that's like, yeah, I mean 2 pi A, 2 pi r, that's right. Okay? Okay? And I didn't write my square on the A's here as anticipated. You're going to end up with an A in the denominator, but best to wait until we actually do. Okay, make sense? So that's pretty simple.